all know a guy who only occasionally shaves for big occasions, and it's because that occasional shave really hurts. It's the time of year for big occasions, and yet there he is, suffering with that cheap drugstore razor. Let's help him out. Henson Shaving's line of razors, built with aerospace precision, deliver a smooth shave your dad, brother, and even son can enjoy, eventually. With replacement blades just 10 cents each, you'll buy it once, and they'll use it for life. How's that for the perfect gift? Celebrate with 100 free blades on your first purchase, and no subscription headaches. HensonShaving.com/holiday.
This morning in North Carolina, wheels are spinning. Determination is winning. A passion is now a thriving business, and it shows no signs of slowing down. How? The power of a conversation, like the one Clint Spiegel had with First Horizon Bank about starting a bike wheel manufacturing facility in Asheville. Now it's not just talk, it's rubber meets road. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Clint. First Horizon Bank, member FDIC.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast known as Space Nuts. My name's Andrew Dunkley, and joining me as always is astronomer Fred Watson. G'day, Fred.
G'day, Andrew. How are you going?
I am well, and you're in sunny Coonabarabran today.
I am, yeah. I don't know whether you can hear it, but there's just getting the buzz of the roller being run over the bowling greens in the Coonabarabran Bowling Club.
And we will hear the occasional road train because they have the big B doubles going past where you're staying. So if anyone hears a rumble, it's not Fred's stomach.
Well, it could be that as well.
Could be that as well. Now, today we're dedicating episode 120 to answering people's questions, which is going to be a lot of fun because we've had some real doozies come in. And we're going to do something towards the end of the program today that we've only done once before. We're going to tackle a movie and talk about some of the theories that were brought up in the film Interstellar. Somebody specifically asked us to talk about some of the concepts in that film, and so we're going to try and do that. It was a great film, one of my all-time favourites, to be honest, but we'll get onto that. We're also going to find out about, this confuses me greatly, and I won't deny that I have absolutely no clue what he's asking you, but it's something to do with the moon and the sunlight and shooting arrows and lines in the sky, and so we'll get onto Simon's question in a moment. And Yannick from Edinburgh is also asking complicated questions about multiple dimensions, particle physics, and the Casimir effect. Thanks, Yannick. It's great. Really appreciate it. But first, let's see if we can answer Simon Anthony's question. And I got a feeling he's being a little bit smug with you, Fred, the way he's written this, but text can be deceptive.
None of our listeners could possibly be smug. So.
I don't know. I think he thinks he's got you tricked. Here's a question for you. If you look at the moon in the daytime and draw a mental line between the terminator points of the crescent-lit side of the moon, I would expect that a 90-degree line of sight from the middle of the line I just drew would point directly at the sun. That is where the light is coming from, right? Well, it doesn't. How come? Now, that's not the end of the question. My photograph shows the expected direction, which in the pic is horizontal, and the actual one, which shoots off the top of the image, getting somewhere near the source of the light that created the shadow it has been extended from. This is very obvious, a very obvious thing to see. If you look, why has this not been recorded in history, and why isn't it widely explained already? I've found some complex and confusing explanations and some ludicrous ones online, but even these are hard to find. It's true from both hemispheres. I've got a UK photo that shows the same effect taken 5 years ago. You can't see the moon in the upside down with respect to the other, but it is. Go on, answer that, please. I hope I put the right inflection on that. Look, it's a long question, and obviously it's something that he's seen in photographs. The light source doesn't line up, I think, is the simple explanation, and he wonders why, and it's never been recorded in history. However, Simon, I can tell you, I know one man who recorded it in a book. Do you know who I'm talking about, Fred?
Page 131 of a book called Why is Uranus Upside Down? And Other Questions About the Universe.
Written by?
Somebody with a very similar name to me, that's right. It was published in 2007, and there is both an Australian and a UK edition, and the diagram of exactly what Simon is talking about.
And the answer to the question, Simon, is buy the book.
Yeah, that's right. Buy the book. It was one of the few. There was about half a dozen diagrams when it went into a UK edition. Of course, all the phenomena are different in the Northern Hemisphere, and I had to redraw the diagram for exactly what Simon's talking about in order to make it work for the Northern Hemisphere. I'm going to cut to the chase because I'm just going to cheat with this one, Andrew, and read out my answer. But by the way, just to explain, there is a precedent for this. So Why is Uranus Upside Down? The book is actually a book of, I think there's about 148 questions that we had on ABC Radio, actually mostly when I was talking to one of your colleagues, Lisa Hampshire.
Oh, yes.
It was years and years ago when I used to do an hour-long segment with Lisa on the ABC. But you and I had questions which appeared in this book as well. So Why is Uranus Upside Down? The title is one of the questions, was about listener questions that we'd already had. And somebody else, Simon, had already asked this question, which is, why does the illuminated part of the crescent moon seem to point above the sun? Okay, here we go.
Why did you say it like that, Simon? Would have been easier for me to understand. But look, I get where he's coming from.
No, Simon, your question is well taken, and it's a good question, and that's why it went into this book. But let me read the answer. This is, in effect, best observed in the afternoon sky when the moon's phase is a day or two before first quarter. The moon then has the shape of a broad crescent, but it's sufficiently far from the sun for the phenomenon to be really noticeable. And I'm afraid I have to resort to rather poetic metaphors to describe it, so I hope you'll bear with me. God, did I write that?
Yeah, it sounds like it.
Yeah. If you imagine the crescent moon as a bow shooting an arrow, then the arrow will point towards the sun naturally, since the bow is simply the side of the moon illuminated by the sun. But when the moon is a reasonable distance from the sun, the arrow points in the direction which, if extended across the sky in a straight line, would pass above the sun. And the reason for this is to do with perspective. Light rays from the sun travel in straight lines, of course, but when they go from one side of the sky to the other, they appear to arch upwards rather than simply traveling parallel to the horizon. In fact, they form great circles on the spherical surface of the sky, which, by the way, is usually known as the celestial sphere because it also includes that part of the sky that lies beneath the horizon. A great circle is the shortest distance between 2 points on a sphere, and on a globe of the Earth, for example, it appears to be a straight line when viewed from the correct angle. But it curves with respect to the equator, and the situation is the same with the sky. When you follow the direction of the arrow from the bow of the crescent moon to the sun, you have to imagine it following a curved path through the sky rather than a straight line parallel to the horizon. And then you'll see it's pointing in the right direction. Wait for this bit, Andrew.
Okay, this is going to be beautiful.
I'm sorry to have to tell you that no one to whom I've given this explanation has ever believed it, so I'm clearly not explaining it very well. However, it is the correct one. Trust me.
So it's an optical perspective.
It's a perspective effect. That's right. Yeah. And look, you can sort of imagine it in a similar way. You know, the classic perspective simile is if you're standing in the middle of a railway track. Don't do it when there's a train coming. Okay, stand in the middle of the railway track. You look one way and the railway lines seem to converge to a point on the horizon. Turn round and look the other way. These are, if you've got a dead straight railway track, of course. Turn round and look the other way, and they'll converge to a point on the other horizon, which tells you that there's a curvature in perspective between the two, because otherwise it just doesn't make sense. And that's exactly what's happening here with the light to the moon. My congratulations to Simon. Not many people do spot this, and it is quite puzzling when you first encounter it. But trust me, the explanation is correct. And there are a lot more questions in why is Uranus upside down? It's still in print. Why don't you go and buy a copy?
Yes, why don't you? I do have a copy. Thanks for the question, Simon. Hopefully we managed to resolve it for you. But it's just the way you're looking at things, basically, is the simple answer. And you can draw all those kinds of effects in different scenarios. So maybe do some experiments on train tracks when they're not being used. Very good. Okay.
Don't do it. He's joking. Okay.
I said when not being used. Wasn't being that cruel. Hopefully. Thank you, Simon. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson, of course. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by Tech Radar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Righto, Fred, to question 2 of our all-question episode of Space Nuts. This one comes from Yannick in your hometown of Edinburgh in Scotlandia. Hey guys, by far my favourite podcast ever. That's because it's the only one he listens to, Fred. Been listening for years, just never decided to get in touch until now. My reason for getting in touch is my paranoia that you will both cease to continue your delightful weekly chinwags. Yeah, well, we hate each other so much, it's probable. Anyway, we'll get past all that because he's really keen for us not to stop, Fred. He says, I have 2 questions, which actually turns into about 5. So here we go. The universe might go awry if not for the familiar 3 dimensions, but theories of everything say there should be more. What are we missing? He also asks, in quantum physics, a particle can be in 2 places at once. Does that mean we can be in 2 places at once? And question 3, the Casimir effect suggests that the vacuum is fizzling with ephemeral particles. Is this real? And can we harness this energy concealed in empty space? I'd be over the moon if you gave me a shout on your podcast. Yannick! Is that good enough? Thanks for your time, Yannick. And yes, we'll try and tackle these questions. So the first one, the universe might go awry if not for the familiar three dimensions, but theories of everything say there should be more. What are we missing?
One thing we missed, Andrew, there is a lovely segue from the previous question, because Yannick will be over the moon too, just like the
good one, Fred.
Yeah. Okay. So basically, how many dimensions are there in the universe? And the bottom line is, and Yannick's kind of, is clearly switched on to what's going on in physics here. We really don't know. Our normal experience says there are three dimensions of space. And since 1905, when Einstein published his special theory of relativity, and actually some work by various mathematicians not long after that, we've realized that time is also a dimension. It turns, if you ever get a chance to look at the equations of special relativity, and I'm sure you do this every morning, Andrew.
I do.
It is beautiful the way that you can see just by looking at the equations that time is actually a dimension. Just like space, the three dimensions of space. But of course, it is different. It shows up differently actually in the equations too, because it's got a negative sign, which tells you there's something different about it from up and down, side to side, and backwards and forwards. So that our normal experience, everyday experience, means we experience these four dimensions. Now, already you can see there's something weird going on here, because if time is a dimension, just like space, why can't we just whiz around in time? We clearly can't do that, and we only experience time, second by second, basically, or sometimes minute by minute, depending on how switched on you are. So there is obviously something a little bit weird going on there, and Yannick's point is absolutely right. If you look at some of the more esoteric theories of the way the universe works, they do suggest that you need more dimensions. Why do you need esoteric theories of everything? The answer is that the two major theories of how the universe works, one on the largest scales, which is relativity, and one on the smallest scales, which is quantum theory, those two theories are incompatible. They actually can't work together, and in particular, they can't work together at the time of the Big Bang. And so we know that there are missing bits of that. We also know from studies of things like dark matter and dark energy, which you and I have talked about interminably, Andrew, we also know that we have an incomplete view of reality, because our current view of reality does not account for those phenomena, which are well observed in astronomy. We know that there is something that outweighs normal matter by 5 to 1 in the universe and tends to pull galaxies together, but we can't see it. We can't detect it other than its gravitational force. And we know that there's something pushing the universe to expand ever more rapidly, which we call dark energy. We've even less idea what that is. So we're clearly missing something. And most of the theories that are being drawn up to try and account for this, and there are very many of them, most of them basically have to resort to more than three dimensions. The most common are string theories, which say that the subatomic particles that make up the universe are not just particles; they're little vibrating bits of string, and string in a very esoteric term of the word. They demand many higher dimensions. In fact, I think the best string theories have either, now I might have these figures wrong, but it's something like they have either 11, 12 or 26 dimensions. Take your pick. Yeah, so they're many, many more than just the three of space and one of time that we perceive. And the way that the theories sort of imagine these dimensions is that they are, and this is the technical term, Andrew, I know it sounds daft, but it is the technical term, they are compactified. And compactified means that
I take a supplement to try and stop that from happening.
Yeah. Yeah, that's right. Hope you take it every morning.
Yes.
Good. Well, moving on from that, the way the string theorists imagine it is that if you think of this is the analog that they always use. Think of a hose pipe, a garden hose pipe.
Mm-hmm.
When you look at it from a long way away, it's got one dimension. It's just something that has length and nothing else, because you can't see its thickness. But if you get close to it, you can see it's actually got two dimensions, because there's the long dimension, but there's also a dimension that goes around, and I'm doing this hand movements here, which I'm sure you can see, but the listeners can't.
I'm doing it too so they can see it.
Sorry, the listener can't. The other dimension is around the circumference, if you like, of the hose, and this is how string theorists at least see these dimensions basically made very, very small. There are other theories as well. There's something called M theory, and M theory is a relative of strings, but nobody really knows what the M stands for. Probably membrane. Some people say it stands for magic. Some people say it stands for mystery. Some mother theory has been, one of the other things. It doesn't really have a meaning. It's just got a name. But M theory says that our universe exists in a 5-dimensional space. Basically, we only see the 4 dimensions of space and time, but the universe itself is floating in this 5-dimensional space. And when you look at it in a 5-dimensional space, it's actually a membrane so it's a thin sheet rather than a 3-dimensional object. And in fact, one of the theories of the origin of the universe, the Big Bang, is called the ekpyrotic theory. It's a great name. It suggests that the Big Bang occurred when 2 of these membranes collide together, our membrane and somebody else's membrane.
Interesting.
Yeah, the thing that freaks me out about the M theory, though, is that at least one of the calculations I've seen says that these membranes are typically separated by only 1/10 of a millimeter in the 5th dimension.
So you would think it probably could have happened again if that's the case.
Sounds awfully close to me, does that?
Yeah,
so,
it does.
So Yannick, the bottom line is, your question is, what are we missing? We don't know, but we clearly are missing something, and there is a huge amount of work going on to try and understand what it is.
We could have saved 4 hours by just saying to him, we don't know. So question 2, we've burned a fair bit of clock here, but we'll keep going. In quantum physics, a particle can be in 2 places at once. Does that mean we can be in 2 places at once?
Maybe.
Well, you and I sort of technically are at the moment.
We always are. Actually, sometimes, well, never mind. Sometimes I'm trying to be in 3 places at once. Wouldn't it be marvellous if we could be in 2 places at once? It would save so many problems.
Well, I'd have a damn good golf handicap.
You might do, yeah. You might have all kinds of things. Okay, it is correct that a particle in quantum physics in what's called a state of superposition, and what that means is that it is essentially isolated from its surroundings. We don't know where it is, and it can be in 2 places at once, and we can demonstrate that relatively straightforwardly using optics, an experiment called the double slit experiment. If you pass if you get single photons of light and pass them through a pair of slits, the photon goes through both of them, and you can prove that by what happens at the other side. So that certainly works.
We all know a guy who only occasionally shaves for big occasions, and it's because that occasional shave really hurts. It's the time of year for big occasions, and yet there he is, suffering with that cheap drugstore razor. Let's help him out. Henson Shaving's line of razors, built with aerospace precision, deliver a smooth shave your dad, brother, and even son can enjoy, eventually. With replacement blades just 10 cents each, you'll buy it once, and they'll use it for life. How's that for the perfect gift? Celebrate with 100 free blades on your first purchase, and no subscription headaches. HensonShaving.com/holiday.
There are experiments which are attempting to take much bigger collections of atoms and molecules rather than just them one at a time, and show that they too can exist in a state of superposition. An experiment probably conducted 8 or 9 years ago now, maybe even a decade ago. It made a microscopic tuning fork. out of, very, very thin sheet of
Oh, I remember this.
Yeah, I think you and I spoke about
Yes.
it. That's right, on the radio, and you could demonstrate that this tuning fork was both vibrating and not vibrating at the same time. There have been other experiments done similarly, and so what's happening here is the quantum superposition effect, i.e., being in two places at once or being in two states at once, that is being extended from just single particles to much bigger collections of particles. So you might say, well, what's to stop it extending to us in the end? And probably the real killer on this is that in order for the superposition phenomenon to take place, you have to be completely isolated from your surroundings, and we never can be. That's the issue. We are going to be immersed in this seething mass of stuff, the atmosphere for a start, and all the photons that are charging around in the atmosphere, all of that would simply destroy quantum superposition.
Okay, so far we've answered two of Yannick's questions with we don't know and no.
Yeah, and finally the Casimir effect.
Yes.
Well observed. Exactly that the vacuum is fizzing with ephemeral particles. They come into and go out of existence. It's actually well studied in basically in particle physics, also in astronomy, because it's this idea of the vacuum seething with virtual particles that causes black holes to evaporate, which of course was Stephen Hawking's great contribution to physics in the 1970s. So it was proposed actually by Hendrik Casimir back in the 1940s, and the upshot of it is if you get two plates of metal, place them very, very close together in a vacuum where there's nothing else going on, they will actually have a force pushing them together. And that force is coming about because around them, the vacuum is creating these virtual particles and then swallowing them up again. They're popping in and out of existence, all these virtual particles, just like my hands are doing now, Andrew, as I'm sure you can see. And that pushes the plates together. So it is a well-observed phenomenon. The theory behind it is pretty difficult. I've looked at some of the equations and they didn't really switch me on very much because I didn't understand them. But it's basically a quantum effect. It's like the other question that that Yannick has asked. It's all about the quantum universe. Once again, that interface between relativity and quantum theory, which really is not working terribly well.
Okay, so I think the second half of that question is, can we harness this energy?
Yeah. Yes, I think to some extent, but it tends to be harnessed in terms of just simply scientific measurement. It's tempting to say, well, is this related to dark energy, which is the energy that's causing the universe to expand ever more rapidly? But I think all the observations, all the theories of dark energy already take the Casimir effect into account, and the answer is no. So I think the bottom line is not really. Practically, it's not going to work.
Yannick, thank you for your questions, and the answers were we don't know,
no,
yes,
no.
And no.
Yeah, that's right.
Basically. But we do appreciate you sending it through. It was really insightful, very, very intelligent question. Much appreciated. You're listening to Space Nuts, of course. Andrew Dunkley here with Fred Watson.
Okay, we checked all four systems and keying with a go.
Space Nuts.
Finally, Fred, our last question of the day in the all-question episode of Space Nuts. This is from Nima in Sweden. Hey, I'm a big fan from Sweden. It's lucky I said he was from Sweden then. Found your podcast totally randomly a few months ago and have been listening to you guys every night while sleeping.
The best way.
So he knows I snore. Was thinking if you guys could do one podcast session where you discuss the science of the movie Interstellar. I know you've mentioned it a little bit about it before, but this time if you could go deeper into detail and discussion about the time difference, time travel, black holes, wormholes, etc. I think you guys would be perfectly. It would be perfect just randomly talking about it. Thanks, Nima. Yeah, look, I loved this film, and Fred hasn't seen it, so I'm going to have to spoon feed him some concepts. But if we can
yeah, it's not quite true actually. I did see it. I did watch it, but
you didn't understand it.
Well, partly, yeah. There's this phenomenon takes place in my head that where if it's a piece of music, I can recall it 10 decades later. But if it's a movie, it comes in one eye and goes out the other. So you might have to, as you said, you might have to remind me of the salient features of the plot.
Right.
I do remember it.
In short, the Earth has died, and they have to get humans off the planet.
Yeah.
And the way to do that is to find somewhere new to live. But before they can do that, they have to evacuate the planet, and that means solving the problem of gravity so that they can get space stations into space. And by coincidence, a wormhole appears near Jupiter, I think. And so they send missions through the wormhole to find a new place to live. And it is during these missions, one in particular, that we start seeing these issues of time and gravity and black holes and wormholes and all that sort of guff. One incident in particular that you and I have discussed was when they were very close to a black hole and had to go down onto the surface of a planet. Now, they parked their spaceship out of the reach of the black hole's effect, but they had to travel down on a smaller shuttle to the planet's surface. But it was under the effect of the black hole, and therefore every hour on the surface of the planet equated to 7 years Earth time. And they were down there for 4 hours, so 28 years elapsed on the spaceship. That's the scenario that we've talked about and which came up. So I suppose we can focus on that one first, the effect of a black hole's gravity in distorting time. It is a known phenomenon, is it not?
Oh, absolutely. That's right. And just as like a preface, Andrew, to these comments, the one thing Interstellar has in its favour is that it was done with the consultancy of one of the world's leading physicists on relativity and gravitational physics, and that's Kip Thorne, a very well-known name in the world of science, a theoretical physicist. He won a Nobel Prize, so he's pretty genuine, good value stuff for this.
Well, and as a layman, Fred, who watched the film, I can tell. I mean, because some of the stuff they did was so believable.
Yeah, that's right. So, so he provided the theoretical background, and in a way, though, one of the curious things about certainly about relativity and quantum theory, they both have aspects which are really quite unbelievable, even though we know they work, and we know from experiments that have been done, yes, that things can be in two places at the same time, yes, that time slows down if you're getting near the speed of light. All of those things have been demonstrated there. And so what was really great about the Interstellar movie was the fact that it wasn't just ideas pulled out of the air. It did have the backing of a world-leading physicist in doing that. So coming to the particular point that you've made, yes, in a gravitational field, your time slows down as seen by an outside observer. And so that's the bottom line. It's that you've got two separate, what are called reference frames. The reference frames are what you carry with you all the time, and they're different depending on the state of your proximity to a gravitating body like the Earth, and they're also different depending on your relative speed. So that was Einstein's special theory of relativity. As things get near the speed of light relative to one another, you start seeing all these weird effects, including time dilation, the time slowing down. So that's absolutely on the money. The one thing, one recollection I have in the movie was of a gigantic wave on the surface of an ocean.
That same planet, actually.
Yeah, and that was being raised because of the high degree of gravitation that was involved. And I sort of slightly balked at that, partly because if you had a wave doing that, the atmosphere would have also done very peculiar things because of the gravitational pull, as would the individuals. The gravitational difference between your head and your feet when you're in such a strong gravitational field would tend to do what black holes do to you, which is to spaghettify you. Basically put strains on your body that we don't experience here. But if you can, let that one go, then it's all great. And a big wave certainly looked pretty impressive. And I have another recollection from the movie of some sort of space-time grid that they were wandering around in. Was that right at the end of the movie?
Yeah, that was after they went into the black hole and went into what was created by an unknown entity, which turned out to be several rooms which were all the same room, but they were multi-dimensional. And it was a puzzle for him to solve, to try and communicate with his daughter, to give her the equation to solve the problem of gravity to get humans off the Earth.
Okay. So multi-dimensional rooms. I mean, we've kind of already touched on this in this session, in this edition of Space Nuts, with the question that we were discussing at the beginning, Simon's question, that multiple dimensions may well exist. I mean, we talked in that about them being compactified when we're talking about Simon's question, but it is possible that they may not be compactified. In fact, M-theory says that the fifth dimension is something that our universe is immersed in. And that would probably fit in with the kind of thing that was depicted towards the end of Interstellar. I mean, the key to the problem they were trying to solve was that of gravity. But the other factor involved was using gravity as a form of communication, as a focal point of A, demonstrating that something was possible, and B, being able to use that through dimensional space to communicate in a rudimentary fashion. Look, we can safely say that the part where he flew his spaceship through a black hole was an absolute farce. I think we could safely say that, could we not? It may be so. That was so farcical, it's completely been wiped from my memory. I don't actually remember him doing that.
That's how he ended up finding the unsolvable theory of quantum, getting the quantum formula to solve the problem of gravity.
Okay, all right.
That was the science fiction side of the story. Wormholes?
Yeah, wormholes are allowed in relativity. The idea that a black hole distorts space to such an extent that there could be a connection through to something that we call a white hole, which is a black hole with all the signs reversed. And white holes, once again, are allowed in the theory of relativity because these things are all symmetric. So wormholes between white holes and black holes could theoretically exist. We have never, ever seen any evidence for the existence of a white hole in the observable universe, and neither have we seen any evidence for the existence of a wormhole. So,
this one was actually created by whoever or whatever was trying to help us, and it was a sphere. Yeah.
Usually we envisage them as a kind of, almost like a tornado.
Doorway.
We're having a passage from one bit of the universe to the other. Theoretically, it all could work, but we have no evidence that these things exist in reality, whereas we do have plenty of evidence that black holes exist.
And the other factor that Nima asks about is time travel. Well, it wasn't so much portrayed in the film as time augmentation, but there have been experiments that show that time can be altered when you use two atomic clocks and keep one on the ground and fly one in a plane, and they come back with the times are slightly different. Yeah. And they did another one with atomic clocks on the top of a mountain, I think you and I talked about not so long ago.
Yes, that's right, indeed.
That's the same thing happened.
Time. Yeah. Look, time travel is absolutely possible as long as you're going forward. And you do it by exactly what you've said. You send your spacecraft off at nearly the speed of light. The figures I have in my mind.
The twin theory. The twin
theory.
That's right. One stays on the ground and the other one flies near the speed of light for I don't know how long and comes back 2 years, I think, and he comes back and he's 2 years older, but his brother's 40 years older or something weird like that.
Right. Exactly right. So the example I always give is if you travel to Betelgeuse, the red star in the constellation of Orion, which, if I remember rightly, is about 500 light years away. You go to 99.999995% or thereabouts of the speed of light. Then you turn around and come back. You have aged, because you're going at that speed, you've aged 10 years, but the Earth has aged 1,000 years because you've gone 1,000 light years. And that's a way of traveling in time to the future. But apart from some really weird ideas that Richard Gott, who is another gravitational physicist, put together about how you might travel backwards in time using
a vacuum cleaner.
Yeah, it was almost a vacuum cleaner. It was two cosmic strings passing one another at nearly the speed of light. Oh my word. We've got no way of going backwards in time. That's the bottom line. So time travel backwards, for my money, is completely ruled out by the physics.
So what's done is done, basically.
Yeah, once you've done it, you're stuffed.
Yeah, indeed. Nima, thank you so much for asking us to talk about that movie. I've been busting to talk about it for ages, and there were several other concepts in it that were worth talking about, but you've nailed the big ones, and that's been a lot of fun. So thank you very, very much. And thank you, Fred, as always, and for making some of these very complicated concepts easy for me to understand. And if I understood them, then everybody did.
It's a pleasure, Andrew. Always great to talk, and I look forward to our next one.
We'll catch you soon. Fred Watson, astronomer, talks to us every week on the podcast known as Space Nuts. Hope you enjoyed the all Q&A edition, and we'll be back again next week. See you then.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.
We all know a guy who only occasionally shaves for big occasions, and it's because that occasional shave really hurts. It's the time of year for big occasions, and yet there he is, suffering with that cheap drugstore razor. Let's help him out. Henson Shaving's line of razors, built with aerospace precision, deliver a smooth shave your dad, brother, and even son can enjoy, eventually. With replacement blades just 10 cents each, you'll buy it once, and they'll use it for life. How's that for the perfect gift? Celebrate with 100 free blades on your first purchase, and no subscription headaches. HensonShaving.com/holiday.
CuriosityStream is the streaming service for people who want to know more. And now check out Curiosity's new series, The Real Wild West. Rolling Stone magazine says it's the history of the West they usually don't teach you.
The mythology of the West left out a lot of the people.
People said they'd never seen a black cowboy. This is the history book, but did you know about these other facts?
Watch The Real Wild West now on CuriosityStream. With monthly, annual, and bundled plans, find the one that works for you at CuriosityStream.com.